Okay, so if you watched the previous videos in this series, you've gotten a little bit familiarized with the concept of molarity and moles, maybe a little bit familiar with moles. We're going to go into moles and molarity in these practice problems because a lot of times you can understand the concept, but then once you sit down to actually apply the information and work the practice problems or work a problem in a test, a lot of us have a problem sitting down and like actually understanding what the question means and what formula to apply to it and how to actually solve the problem. So I wanted to do this video in the molarity series, just working problems, and take it one step at a time so you can see that there's nothing to be scared of. There's just some problems just have a lot of steps in them. It's really basic math. There's no fancy algebra or anything in it, and you can do this. So let's look at this first problem. We have 22.6 grams of C12H22O11. Now you see this C12H22O11. This is all written together with no spaces because this is all one thing. This is all one substance, one molecule, one compound. And the way these are written is that the little number, see like the 12 right here, the little number that's kind of lower than everything else, that only applies to the element directly before it. So this 12 only applies to the letter C, which is carbon. So this little 22 here, this 22 only applies to hydrogen. And this 11 only applies to oxygen. So when you see these little numbers down here, we call them a subscript. Subscript. Or sometimes somebody will say, a science teacher might say, carbon sub 12. So, or C sub 12. And that just means this. So that just means 12 of carbons. 12 carbons. Okay, so let's get into solving some of these. Okay, so for this molecule C12H22O11, that is put together, just like you build a house with Legos. The Legos that get added together to make this molecule are 12 carbons, 22 hydrogens, and 11 oxygens. And we know that because those are the little subscript numbers next to each of those elements. What we're trying to do here is we need to figure out how many grams of C12H22O11 are in 1 mole of C12H22O11. So how many grams are in 1 mole of this molecule? So let's start with carbon. We have 12 carbons, and let's go to our periodic table. You have to do this with the periodic table. So here's our periodic table, and here is our carbon right here, kind of on the right-hand side of the periodic table. Now, if you look at the bottom of that square, there's a number there, and it says 12.01. That is the atomic weight. So the atomic weight of carbon is 12.01. Well, what does that mean? Well, that means if you have 12.01 grams of carbon, that means you have 1 mole of carbon. So we found out the weight of 1 mole of carbon is 12.01 grams. But we don't have 1 mole of carbon, do we? We have 12 moles of carbon. So we need to take this 12.01 grams per 1 mole of carbon and we need to multiply it by 12. So 12.01 grams times 12 is 144.12. So that means 144.12 grams of carbon equals 1 mole of carbon sub 12, or 1 mole of 12 carbons. So that's 144.12 grams. Let's go back to our worksheet and write that down. So 144.12 grams of carbon equals 12 moles of carbon. Now, let's do hydrogens. We have 22 hydrogens. So let's go over to the periodic table. And hydrogen is up in the upper left-hand corner. And if you look at the number on the bottom of the square, that says 1.01. So 1.01 grams equals 1 mole of hydrogen. But we don't have 1 mole of hydrogen that we're dealing with, do we? We have 22 moles of hydrogen that we're dealing with. So we need to take this 1.01 grams and multiply it by the 22 hydrogens we have. And that'll give you 22.22 grams of hydrogen equals 1 mole of H sub 22, of 1 mole of 22 hydrogens. So let's take that 22.22 grams back to our worksheet, and we'll put 22.22 grams of hydrogen equals 22 hydrogens. Now we need to do the oxygens, and there are 11 oxygens that we're dealing with. Remember, because in the original molecule formula that was given to us, there's a little tiny 11 next to the O, and the little tiny 11 applies to that element that comes right before it, which is oxygen. So that means we have 11 oxygens we need to deal with. So here's oxygen over here, kind of on the right of the periodic table. And its number, its atomic mass unit, is what it's called, atomic mass unit, or atomic weight. Or atomic mass. These could be called any of these three, and they're still just talking about the weight down here on the bottom of the square, the 16.00. So 16.00 grams of oxygen equals 1 mole of oxygen. But we're not dealing with 1 mole of oxygen, we're dealing with 11 moles of oxygen. So we need to take that times 11. So 16 times 11 is 176. So that means 176 grams equals 1 mole of O sub 11, or of 11 moles of oxygen. Now let's take this 176 grams back to our worksheet, and we'll put down here 176.00 grams of oxygen equals 11 moles of oxygen. Now we just need to take these grams that we found out is equal to the moles of the elements that we need, and we just need to add them together. So if you take 144.12 plus 22.22 plus 176, you end up with 342.34 grams. So what does that mean exactly? What does this 342.34 grams number mean? That means this 342.34 is 1 mole of C12H22O11, which is in our original problem provided for us. It says calculate the moles in each, and this number 1 is 22.6 grams of C12H22O11. So C12H22O11 is 342.34 grams, and that's in 1 mole. But you don't have 1 mole, do you? You have 22.6 grams. You don't have 342.34 grams. You only have 22.6 grams. So how many moles, or how are we going to find out how many moles or what fraction of a mole do you have if you only have 22.6 grams? Well, we're just going to take the 22.6 grams, and I usually just put it over 1 because it makes things less complicated, because then it lines up. Then you have something over 1 here and 1 mole over a number right here, so they match. So I just put the 22.6 grams over 1, and then I just multiply them. So you don't even have to do anything fancy like cross multiply or anything. You just multiply straight across. So you just multiply 22.6 times 1, and let me erase this, and that equals 22.6, and that's on the top of the fraction bar. And then you take the 1 times 342.34, and then you get your calculator out and you divide 22.6 divided by 342.34, and you get 0.06, and you get 0.066. So what does this number mean? This is how many moles of C12H22O11 that you have when you only have 22.6 grams of it. You have 0.066 moles. So now let's move on to our next problem. A different color here. We have 42.6 grams of sodium chloride. And this, by the way, is just table salt. Sodium chloride. Sodium chloride. So remember the table salt example I was giving you in the other video, in the previous video? So this is the same thing. This is sodium chloride, table salt. So we are just making salt water in this problem. So we need to find out, before we do anything with this 42.6 grams, first we just need to take that NaCl and we need to find out how many grams of sodium chloride are in 1 mole of sodium chloride. So we know that NaCl is Na plus Cl. And since there's no little numbers down here, remember up here on number 1, there's the C12, the H22, and the O11 up here after the elements, abbreviations, there's nothing down here after sodium. This is blank. There's nothing after chlorine either. It's blank. So that means that it's implied that it's just a 1. So if there's a 1, nobody's going to write Na1, chlorine 1. Nobody writes that. So they're just going to leave it blank like that. And so you just have to know that that means 1 and 1 down there. So there is 1 mole of sodium and 1 mole of chlorine equals 1 mole of sodium chloride. So we need to find out what this mole is going to weigh in grams. So let's do the 1 mole of sodium first. Let's go to the periodic table. And here's sodium on the left. And sodium's atomic mass is 22.99. So that's 22.99 grams in 1 mole of sodium. And that's what we need, right? We need 1 mole of sodium for sodium chloride. Now, if you look on the right of the periodic table, chlorine is over here in the 7th column, and chlorine's atomic mass is 35.45. 35.45. So that means 35.45 grams is going to equal 1 mole of chlorine. Well, didn't we say that sodium chloride is 1 mole of sodium plus 1 mole of chlorine? So if we take this 1 mole of sodium, this 22.99 grams, and this 1 mole of chlorine, this 35.45 grams, and we just add them together, then that's going to give us how many grams is in 1 mole of sodium chloride. So if you add them together, that gives us 58.44 grams of sodium chloride equals 1 mole of sodium chloride. So let's take this answer, this 58.44, back to our worksheet. And so we have 58.44 grams of sodium chloride equals 1 mole of sodium chloride. But we don't have 58.44 grams, do we? Because now we can go back to our original problem. And our original problem, it says we only have 42.6 grams of sodium chloride. So 42.6 grams is less than 58.44 that's in 1 mole of sodium chloride. So we have less than 1 mole. So how do we find out how much of that mole do we have with this 42.6 grams? Well, as I did before, I took the 42.6 grams and I've just put it over 1 because I think it's less. Sometimes you'll see people who will just write 42.6 grams times 1 over 58.44. Well, I think that's kind of confusing. So what I do is I make everything over something else. I make everything into a fraction, 42.6 over 1, and then I times it, and then 1 mole of sodium chloride is 58.44 grams. And so then we just multiply this together. So we just multiply straight across. We go 42 times 42.6 times 1 mole. And so that equals 42.6. And then 1 times 58.44, well, that's 58.44. Now you get out your calculator and you divide 42.6 divided by 58.44, and you should get 0.7 And I rounded that. It's a longer number, but I rounded it to 7.729. It's actually like 0.728952772. So if you get that, don't panic. You got the right number. I just rounded it to 0.729 to four significant figures. So what does that mean? 0.729. What does that mean? Well, that means that you have 0.729 moles of sodium chloride if you only have 42.6 grams of it. So if you have 42.6 grams of sodium chloride, then you don't have a whole mole, you have 0.729. Okay, so now let's go on to our next problem. Number 3 is 315 milligrams of C6H12O6. Well, don't worry about the 315 milligrams yet, because what we need to focus on first is we have this molecule right here, C6H12O6, and we need to find out how many grams of this is equal to 1 mole of it. So how many grams makes a mole of C6H12O6? So you should be getting the hang of it by now that these little tiny numbers in front of each of the elements, they only apply to that one element that's before it. It doesn't apply to anything else in the formula or in the molecule. So that 6 only applies to the carbon. So we have 6 carbons. And then this 12, this only applies to the hydrogens. So we have 12 hydrogens. And then this 6 over here only applies to the oxygen. So that means we have 6 oxygens. So we have 6 carbons, 12 hydrogens, and 6 oxygens in this molecule. So first let's do the carbons. We have 6 carbons we need to worry about. So let's see the periodic table. So carbon is kind of on the right hand side. It's like it's in column number 4 in group A. And here is the number at the bottom of the square, 12.01. So 12.01 grams equals 1 mole of carbon. But we don't have 1 mole of carbon, do we? We have 6 moles of carbon. So that means we want to multiply this 12.01 grams times 6 for 6 moles of carbon. So that's going to give you 72.06 grams in 1 mole of carbon sub 6. So let's take this 72.06 grams back to our worksheet. So the 6 carbons is 72.06 grams altogether. And now we need to deal with the 12 hydrogens. Well, we know that hydrogen is 1.01 grams per hydrogen. And so if you take that by the 12, because we have 12 hydrogens, then that's going to give us 12.12 grams in 1 mole of hydrogen sub 12 or 12 hydrogens. So we have 72.06 grams for the 6 carbons. We have 12.12 grams for 12 hydrogens. Now we need to move on to the 6 oxygens that we have. So oxygen is going to be over here to the right of carbon, and oxygen's atomic mass is 16. So that means 16.00 grams is 1 mole of oxygen. But we don't have 1 mole of oxygen, do we? We have 6 moles of oxygen. We have 6 oxygens we need to deal with. So that means we should take the 16 grams that weighs 1 mole of oxygen, and we need to multiply it by the 6 oxygens that we were dealing with in this molecule. So 16 times 6 is 96. So 96 even. So 96 grams is going to equal 1 mole of C sub 6, or of 6 carbons. Oh, and this should be oxygen, not carbon. We have 1 mole of oxygen, of 6 oxygens. So I'm sorry if I confused anybody on that. So let's take this 96 grams that is equals 1 mole of 6 oxygens, 96 grams over to our practice sheet, and let's write in 96 grams, and that's 1 mole of 6 oxygens, O6. The C6, this whole C6 here is 72.06 grams. This H12 here is 12.12 grams. And this O6 here is 96 grams. So all we have to do is add these together. And 72.06 plus 12 plus and 72.06 plus 12.12 plus 96 grams is 180.18. So 180.18 grams is 1 mole of C6H12O6. But do we have 180.18 grams of C6H12O6? Look at what they gave us for however much we have of this molecule. They said 315 milligrams. Now notice this is in milligrams, this isn't in grams. So what we need to do is we need to first convert this 315 milligrams into grams. Now I have other videos on conversion under my Chemistry 1 playlist, my main Chemistry 1 playlist. So if you're not familiar with conversions or you have a hard time with it, then check out my conversion videos. But I'll tell you right now that if you want to convert milligrams to grams or anything, millimeters, anything that starts with milli, you want to just convert it back to a plain old gram or meter or liter or whatever the milli is in front of. If you want to convert milligrams into grams, you just take where the decimal point would be after the 315 and you just move it back 3 spaces. So 315 milligrams equals 0.315 grams. So if that confuses you, then go back to my conversion videos and I'll take a look and check and make sure they're up to date and that they have good examples like this on there. But uh, so if you're confused by that, then look up conversion stuff. But I'm just telling you. But I'm just going to tell you for the sake of time because we're studying molarity, not conversions right now. So we have 0.315 grams of C6H12O6, but we need 180.18 grams to make 1 mole. So how many moles do we have? Obviously, we're going to have less than 1 mole. We're going to have a tiny portion of a mole. So we're going to take that 0.315 grams over 1, and then we're going to multiply it by 1 mole of C6H12O6, which is 180.18 grams. So that means we're going to multiply across. We're going to go 0.315 times 1, so that's 0.315, over 1 times 180.118, so that's 180.18. So now we're going to take our calculator and take 0.315 divided by 180.18. And that should give you 0.001748 because I rounded it to 4 significant figures. It's actually longer than that, but I just rounded it to 4 significant figures. So 0.001748. So what does that number mean? That means that's how many moles you have of C6H12O6 when you only have 315 milligrams of that substance. Now let's go to our next page of problems. And we're going to get into molarity now, into molarity. First, we were just determining what the moles were of everything. Now we're going to determine the molarity. So if you can see, we still have the same numbers. We're still dealing with the same elements and the same numbers. And I even carried over our calculations from page 1 over here, so you have that information already, so we don't have to do it again. So notice there are additional constraints to each problem that's added on now. And that's going to show us how to calculate the molarity of the solution. So as you can see here, we have the same numbers and the same molecules. Number 1, 22.6 grams of C12H22O11. But now we have an additional part to the question in 0.442 liters of solution. And in problem number 2, we still have 42.6 grams of sodium chloride, but now we have it in 1.58 liters of solution. And in number 3, we still have 315 milligrams of C6H12O6, but now we have the additional detail in 58.2 milliliters of solution. So now that we know how much of the solution we have, now we can find the molarity. And the molarity is just the same amount of moles, whatever the molarity is, that's the same amount of moles in the solution out of 1 liter of solution. So it's the number of moles in a solution, the number of moles of the solute. So if we're making salt water, the number of moles we're counting would be the salt, not the water that we're putting in into the solution. Out of 1 liter of water that we add to the solute, that we add to the salt to make the solution. So it's kind of like making, like making salt water. It's like making Kool-Aid or something. You have to take some powder and you put it in 1 liter of water in a pitcher and you mix it up and dissolve it and it turns into a solution. So Kool-Aid is a solution. And as I used the example of making orange juice on our previous examples, that still stands. Exactly what I said on the previous videos with the orange juice. We're taking that exact same concept and we're applying it to moles of molecules, to moles of compounds. And what is a mole really? But it's just the atomic weight on the periodic table in grams, as you found out from our first page of solutions. So let's tackle these problems and don't be worried about it because you'll see that it's not that bad. It's just an extra step. As I said, chemistry is not that hard so much as that it just has several steps to the problems. So you have to be patient and you have to be willing to do all the steps without panicking or freaking out or thinking you're doing it wrong. So now let's do our first problem. We have 22.6 grams of C12H22O11 in 0.442 liters of solution. So that means we have 0.442 liters of the Kool-Aid, or we have 0.442 liters of the orange juice. And, we only put 0.442 liters of water in with the orange juice, or we only put 0.442 liters in with the Kool-Aid powder drink instead of a whole liter. So that's going to make it a lot stronger, isn't it? If you took the orange, like going back to the orange juice concentrate, if the recipe on the can said to add 1 can of orange juice concentrate, the frozen orange juice concentrate, and then add a liter of water and mix it up, but you didn't add a liter of water, you only added 0.442 liters of water, which is less than half of a liter. That orange juice is going to be really strong, isn't it? So we're going to have less, we're going to be adding less water than a liter in this instance. But remember, molarity is all about what's in 1 liter. So if you were to make the same recipe, but you would make a if you would make a liter of it, how many moles would you actually put in that liter of water to make the same strength orange juice, or the same strength, same concentrate orange juice, or the same strength Kool-Aid? So in this, we are only putting 0.442 liters of the solution. So we're going to put that on the bottom of our fraction bar. Because remember, molarity, I'll write it up here, or over here, molarity is the number of moles of something you put in over 1 liter of water. So if we only put in 0.442 liters of water, we need to keep that on the bottom of the fraction. So 0.442 liters on the bottom of the fraction bar, because the molarity is the number of moles over the liter of water. So now we have 0.442 liters on the bottom of the fraction bar. What do we put on the top? Well, we put on the top the number of moles that we're putting into the 0.442 liters of water. Well, where do we get that information? Well, we just did it on the previous page. We found out how many moles we have of C12H22O11 out of this 22.6 grams. So we have 22.6 grams of this, but we had to find out how many moles that was, because now we need to know how many moles we're putting in 0.442 liters of water. So we're going to write 0.066 moles. So we have 0.066 moles in 0.442 liters. Well, we need to find out how many moles, are we going to have if this 0.442 liters was actually 1 liter. Because remember, molarity is all about 1 liter on the bottom of the fraction bar, and then the number of moles on top. So in order to get the molarity, we have to change this 0.442 liters into 1 liter. So how do we do that? Well, and let me erase some of this just so I have room. Let me erase these arrows. So anything divided by that same thing is 1, right? So 2 divided by 2 is 1. 147.5 divided by 147.5 is 1. So how we get this 0.442 liters to turn into 1 liter is we divide it by itself. We divide it by 0.442 liters, and that gives us 1 liter. But what we do to the bottom of this fraction, we have to do to the top. So that means we have to take this 0.066 molarity, and we also have to divide that by 0.442. So if we take our calculator and divide 0.066 divided by 0.442, that's going to give us 0.1493. And so 0.1493, what is that? 0.1493 moles. We would take 0.1493 moles if we were going to put it into 1 liter of water at the same strength of 0.066 moles in 0.442 liters of water. So if we're keeping this the same strength, we're going to use the same recipe. We're just making more of it. We're making a whole liter of it. We would use 0.1493 moles. The way we would write this would be, and I'll write it over here, equals, we would write 0.1493 and then a capital M, and that stands for molarity. And then we would write the C12H22O11 after it. Or sometimes you can just get away with 0.1493 M. Okay, so let's go to our next problem. Okay, let's go to our next problem. We have 42.6 grams of sodium chloride in 1.58 liters of solution. So we already know how many moles 42.6 grams of sodium chloride is, because that's what we have. That's what we have. You act like you're working in a lab, or you're working in the kitchen. You're making salt water, and you go in and you only have 42.6 grams of salt. Well, you figured it out, and you know that's 0.729 moles of sodium chloride. So you know you have 0.729 moles of sodium chloride. And now we have a new detail in the problem. It's telling us how much water we put in with the salt. So we took a picture and we put in 0.729 moles of sodium chloride, and in that picture we put 1.58 liters of water. What we need to do to find the molarity, because remember, molarity is how many moles, the number of moles in 1 liter, of water. So the molarity is number of moles in 1 liter, or over 1 liter, out of 1 liter. So we don't have 1 liter. We're not using 1 liter of water in this recipe. We're using 1.58 liters of water in here. So if we're using 1.58 liters of water with this 0.729 moles of sodium chloride, then that's not going to be near as strong as if we were to use a whole mole in there, or if the molarity was 1. This is kind of diluted. So like if this were Kool-Aid, we would only be adding 0.729 of a packet. We'd only be adding 73% of the packet of Kool-Aid in over 1.5 liters of water. So that would make it really watery. That would make it really dilute, and it wouldn't be strong at all, and the taste would be diluted. So we need to find out what the molarity is, but the molarity is all about the 1 liter of water. So somehow we need to change this 1.58 liter of water to 1 liter of water. And That's how we find out how many moles That's how we find out how many moles of sodium chloride would we add if we were only using 1 liter of water. So, let me erase these. How are we going to find out how many moles of sodium chloride we would add if we had 1 liter of water instead of 1.58 liters of water? Well, we need to turn this 1.58 liters of water into 1 liter of water. And how do we do that? Well, we divide it by itself. We divide it by 1.58 because anything divided by itself is 1. So we divide this 1.58 liter of water by 1.58 liters and we get 1 liter of water. But what you do to the bottom of the fraction, you have to do to the top. So now we have to take this 0.729 moles of sodium chloride and we have to divide it by 1.58. So if you take 0.729 moles of sodium chloride divided by 1.58, you're going to get 0.4614. And I rounded up there. So if you get 0.46139240, you're good. I just rounded to 4 sig figs. So 0.4614, what is that? That is the number of moles you would use if you were using only 1 liter of water. So that means the molarity is 0.4614. So that would be written 0.4614 and then a capital M for molarity, and then after it you can write NaCl. Okay, let's move to our third problem. Our third problem is that we have 315 milligrams of C6H12O6, and remember we converted that 315 milligrams into 0.315 grams. That's a grams on the end of here. And we have 315 or 0.315 grams of C6H12O6. And we worked that out to be 0.001748 moles of C6H12O6. So that's not a lot, is it? That's a very small amount. But now we have a new detail in 58.2 milliliters of solution. So now we know how much water we're adding to this. This is sugar, by the way, C6H12O6. This is a form of sugar. So we're making sugar water in this. So we have, from these moles that we worked out in the previous page, we have 0.001748 moles over 58.2 milliliters of water. Now, do you notice something strange about this 58.2 milliliters of water? Well, that's right. It's in milliliters, not liters. We need this to be in liters. So just like I taught you how to convert anything, millimeters, milliliters, milligrams, if you want to just convert that to plain old liters or meters or grams, you just move the decimal point up 3 places. So we're going to put a 0 there as a placeholder, and there's your decimal, and put a 0 in front of the decimal point, and we get rid of this one. So we actually have 0.0582 liters of water. Now we need to know how to get this 0.001748 moles over 0.0582 liters, and we need to turn this into some number of moles over 1 liter. So how do we do that? Well, we take this amount that we have in liters, the 0.0582 liters, and that's what we divide it by. We divide 0.0582 liters because 0.0582 liters divided by 0.0582 is 1. So we just take that and divide it by itself and you get 1 liter. But what you do on the bottom, you have to do on the top. So we have to take 0.001748 moles that I got from there, and we have to divide that by 0.0582. And if you take out your calculator and you divide 0.001748 divided by 0.0582, then you end up with 0.03. So the answer down here is 0.0300 moles in every 1 liter of water if we were to keep the recipe the same, which means the molarity is 0.0300 capital M, and then you can write C6H12CO6 after it. So that would be your answer. This is the original question was calculate the molarity of each solution, and that's what we did. So we have now we have the molarities for each solution because they gave us the amount of water that we're putting into it. So as long as you know the amount of water you're putting into it, you can figure out the molarity. Now let's go on to the next page.